This is an update to a video I made a while back about plotting rarefaction curves in R. I wanted to make an update because in the old video, which I'll post a link in the description, in the old video I showed how to plot rarefaction curves just using the base R package. But I already had rarefied data, so the data were already generated and so on. I thought it would be useful to have a video showing how to generate rarefied data. So we'll be using the rarefy function in the vegan package in R, and then plot them. And so this will all be in one package, or in one video. So let's get started. So I'll also post this code in the description of the video. So if you want to follow along or adapt the code to your uses, you can do that. Okay, so we're going to start in loading in our data. I'm going to set my working directory here. I have my data here. It's this birds.csv file. Let's have a look at it here. So here, this is breeding bird survey data from the state of Colorado for 2018 and 1978. So here in the first column, we see all of our species, all of our taxa, and our taxa are all in rows. The second column here is the number of individuals of each taxa detected in 2018, and the third column is the number detected in 1978. So 40 years difference in surveys here. So let's just look at some of the basics of the data set. So here, let's just look at the total abundance for each column. So I'm just going to sum each column here. So I'm going to make a variable or an object called abundance 2018. It's just going to be the sum of that column, right? So this is saying from the birds data frame, the $ says select this column. So that the $ says we're going to select the abundance 2018 column. Okay, let's run that. Okay, so we see here our value. So in 2018, there were 63,594 individuals sampled in the 2018 breeding bird survey. Let's do the same thing for 1978, and you see in 1978 there were only 15,905 versus 63,000 individuals in 2018. So this is why you generally use rarefaction. If you've got two samples that you want to compare somehow, you want to compare the diversity of these two samples, and if your abundance varies really greatly, you want to make them more comparable, right? Because imagine if you take a really big sample, you have higher sampling effort, you're more likely to detect rare species in a big sample than in a small sample. So typically we're going to have more species in a larger sample. What we want to do with rarefaction is figure out, is that difference in diversity, in this case we're just going to look at species richness, so is that difference in number of species an artifact of our sampling effort, or is it a real difference between the communities? Disclaimer here, this is not the way to investigate changes in bird diversity from breeding bird survey data. This is just a very simplistic overview to show you how to do rarefaction, right? So don't call me out on sloppy science here. This is just an example. Okay, so let's look at the species richness. So here, the richness for 2018, the way I'm going to do this is use the sum function, and again, the birds data frame and the $ abundance 2018. And then if you do this not equal to 0, it's going to give you a count of the non-zero numbers in that column, right? So that's basically just a tally of the species richness. So we'll just hit enter there, and so we can see in 2018 we had 221 species detected, right, out of 63,594 individuals. With 1978, here we had 143 species. So again, as we'd expect, we have more species with a larger sample and fewer species with a smaller sample. But is that difference real, or is it an artifact of our sampling effort? Okay, so the most common way to do rarefaction these days is using a function in the vegan library. So I'm going to load in the vegan package, library vegan. And then this is what you use. So rarefy. And what I can do is rarefy birds, that birds abundance column again. So the abundance 2018. And what I'm going to do is I'm going to choose 15,905. So that's the number that number of individuals that we detected in 1978. So what if we just take a sample from those 63,594? If we take 15,905 random individuals, how many species are we going to get, right? And we can also set our standard errors to true, and it'll show us not only the estimate of species, but it'll also show us our standard errors. So I'm creating an object called rarefied 2018, which is going to do just that. So let's run it and see what we get. Okay, so here, and I'll just click on it up here, we have a new object here. This is what we see. So our S, our sample estimate, or our species estimate, would be 199.92, right? So about 200 species we would expect if we sampled 15,905 individuals out of the whole 63,594, right? And our standard errors are about 3. So we could expect, between 197 to 203 species if we took that smaller sample. And that's usually all you have to do when you're doing rarefaction, is you want to make those two data sets comparable. However, you might want to plot a rarefaction curve if you're in an ecology class or something to try to understand what's going on when you're doing rarefaction. It's useful, I think, to plot these on a curve and so on. So I'm going to show you how to do that. So what we're going to do is you can not only, so here we did rarefy on just one value. We said take this number of individuals out of this sample, and then how many species do we get? But you can do this over and over again for a whole range, across a whole range of sample sizes, right? So let's do this. So I'm going to create an object called rare2018. I'm going to use that rarefy function. I'm on the 2018 abundance column. But instead, what you can do something like this. You can say, you do this across a range of values, so C1 to 63,594, right? That's our total abundance. So you can do rarefaction across that whole range of values, and then you can plot that on a curve. The problem here is, if you do this, you're basically doing this 63,594 times. You're resampling over and over again. You're going to say take 63,594, then take 63,593, then take 63,592, and so on. That's going to take a long time. In fact, I ran it just to see what would happen, and it took my desktop computer about 20 minutes to run that, that little simulation. So instead, I'm just going to choose about 250 samples. So if we divide 63,594 by 250, we get about 250. So I'm going to do that. So in here, instead of selecting just a number or a range of numbers, I'm going to use the seek function. So seek 1 to 63,594 by 250. So that means every 250 individuals, we're going to take a sample. So that'll leave us with about 250 observations. And then I'm going to set my standard errors to true. So let's run that. Okay, and it takes a couple seconds, right, because it's doing multiple subsampling. And that's what we get. Now, I'm not going to click on this because it gives you a matrix that's really kind of weird. Your columns are where your rows you would expect your rows to be. So I'm going to transpose that matrix first. So here I'm going to create an object called trare2018. And I'm just going to transpose that matrix. So T is transpose, rare2018 is my original matrix. So let's run that. So we've transposed it. Now let's make it a data frame, because those are easier to work with. So rare.2018.df for data frame, right here. So just use the as.dataframe function, and I'm going to use that transpose matrix as my input. So run that one. Now let's look at our data frame. So rare2018 data frame. You see what we have here. With 1, our n is 1 individual, we get 1 species, right? Our .s column here is species, and our standard errors are 0, because we just get 1 species. If we select 251 individuals, the second row here, we get about 76.69 species, so about 77 species, and our standard errors are 4.3. Right? If we select 500 individuals, we get 99 species, and so on and so on. And we've done that all the way down to if we select 63,000, we get 63,501 is our top sample. Right? So again, we get about 255 observations is what we have there. Okay, so this is what we want to plot to make our rarefaction curve. To do that, first we need to, I like to plot the standard errors. So what I'm going to do here is I'm going to make a new column. So in that rare 2018 data frame, I'm going to create a new column, so $, SE high for the high standard errors and SE low for the low standard errors. So for high, I'm just going to take the S column, right, the number of species that we estimate, plus the standard errors. And then down here, I'm going to do the same thing. 2018 sample, the species estimate minus the standard errors. So I'm going to add those two columns to the data frame. Okay. And now if we look at our data frame again, see we've got our two new columns, SE high and SE low. So here, if we take 251 individuals, we get 76 species, and our range is 72.38 to 81. Right? So we can plot all those as separate curves. The other thing we need to do is make a column for our sample size. So I'm going to create another column in there. I'm just going to call it N for our species, or sorry, our individuals. And that's going to be the same thing, right? 1 to 663,594 by 250. Okay. Enter. Okay. So now if we look at our complete data frame, again, so our sample size was over here on the left, and now we have an actual column of those values here that we can use to plot. Okay, so we're going to do the same thing for the 1978 data because we want to compare them on the same graph. In this case, we have 15,905 individuals. So to get about 250 points to plot, I'm going to do that by 64, right? So we're going to take every 64, we're going to divide 15,905 into 64 equal bins, basically. Okay, so new object, rare 1978. We're going to rarefy across that range and set our standard errors to true. Let's run that. It takes about a second. Transpose our matrix there, make a data frame there, add our standard errors there, and then add our sample size. So now if we click on our data frame here, this is the 1978 data. Again, 1, 65, 129, these are our sample sizes, our number of individuals selected. S is our number of species. Here's our standard errors, and so on. Great. So far, so good. Now let's just plot it. So I'm just going to use the plot function. I'm going to plot on the x-axis the N column from rare 2018. And on the y is going to be the S, the species, right? So our x-axis is our abundance, and our y-axis is our species. Type L for a line graph. Xlim, let's make that, we have 63,000 some species, or individuals. So let's just make it 64,000 as our x limit, right? So our x-axis is going to go from 1 to 64,000. Let's make our line width a little thicker. 2. Color, I'm going to use Fire Brick 4, which I like. My x label is abundance, or my y label is species richness, or species. And then I've got a title for the whole thing. Okay, so let's make that plot. Enter. Okay, so here we go. There's our rarefaction curve for 2018. Let's add our standard errors. So we use the lines function. The same thing, our x is going to be our n column. In this case, our y is going to be our standard error high and standard error low. In this case, I'm going to use a dashed line to show my standard errors, and I'm going to use the same color because I'm still dealing with the 2018 data. So add standard error high, standard error low. There we go. Then we continue to use the lines function, and we're going to add the 1978 data. In this case, I'm going to keep everything the same, but I'm going to change it to Dodger blue as the color. So there, and add my standard errors. Let's add a legend. So for legend, you give it the coordinates, the x and y of where you want it to be. So I'm going to put it down in this lower right corner. So let's put it at about 40,000 x, 40,000, and my y, yeah, let's put it maybe, yeah, about 75 sounds good. I'm going to label those 2018 and 1978. I'm going to use the same colors as in the plot, and we'll run it. So there we go. There's our legend right there. Okay, so there's our rarefaction curve. You can play with this, of course. You can change the colors, line thicknesses, and so on. You can also change the axes. I chose 64,000 as my X limit so I could show the very edge of this curve. Notice how these curves both flatten out quite a bit pretty early, right? As we're adding more individuals, we're not getting a lot more species here. So you can play around with that too. What if I cut off my X limit here at about 10,000? Let's see what that plot looks like. So there we go. It's a little bit of a different curve. Notice that this is cut off though. That might matter to you. I can add my standard errors. I can add my other data set there too. So there's a lot of things you can play around with, but that's the basics of how you do rarefaction, how you can do rarefaction across a range of values and plot it.